Welcome to this explainer. Today, I'm basically acting as your virtual architecture consultant to give you a concrete, totally actionable blueprint for selecting your local LLM inference engine. We are looking squarely at the landscape of 2026, where the choices you make for your underlying framework can literally make or break your entire deployment.
So here's the harsh reality right now. Local LLM deployment, it's no longer just some experimental luxury, it's a mandatory architecture layer. But selecting the wrong framework for your specific workload leads to a massive 2 times to 6 times drop in performance on the exact same hardware. You really have to ask yourself, are you currently wasting up to 80% of your GPU's potential simply because of bad routing?
This brilliantly illustrates the stakes here. Standard frameworks just suffer from these severe memory bottlenecks and fragmentation. Think of it like a massive, messy warehouse where you can't find space for new boxes because everything is just scattered randomly. But an optimized engine, it achieves incredible parallel processing, streamlined execution, and pushes your hardware to its absolute limit. Ultimately, your framework dictates your hardware utilization, plain and simple.
Okay, so here's our roadmap for your architecture design today. We're going to move logically from understanding the performance trap of legacy setups, take a rapid-fire tour of the 5 distinct engines dominating the field, build out some hardware-driven deployment scenarios, match specific workloads to these frameworks, and finally, design an intelligent enterprise routing strategy.
Kicking things off with Section 1, the performance trap of local LLMs. Moving right along to Section 2, 5 engines, 5 specialties. Let's look at the actual tools in our arsenal.
First up on our rapid-fire tour, we've got vLLM. Now, what's amazing here is how it dynamically allocates KV cache in modular blocks, usually chunks of about 512 to 2048 tokens. This is essentially mimicking an operating system's virtual memory management. By eliminating fragmentation, vLLM achieves a staggering 95% VRAM utilization. Paired with continuous batching, which instantly slots in new requests rather than waiting for a whole batch to finish, this is absolutely your go-to for high-concurrency production API services deployed on NVIDIA, AMD, or TPU infrastructure.
Next up is SGLang, and this one features a really fascinating radix tree structure. Imagine you've got 50 employees all asking an AI about the exact same 100-page HR policy document. Instead of dumping its memory every single time, SGLang reuses that shared document context by retaining historical request prefixes in a persistent tree structure. This completely bypasses redundant computation, delivering up to a massive 6.4x speedup for complex RAG, multi-turn conversations, and those really intricate AI agent workflows.
Then, of course, there's the true Swiss Army knife of local models, llama.cpp. This framework is wild because it entirely bypasses traditional loading. It utilizes ultra-compressed GGUF files and memory mapping, or MMAP, to load massive 70B models in seconds, natively in pure C++. It has 0 external dependencies, so no CUDA or metal required. You can run massive multi-billion parameter models on everything from a robust server all the way down to a Raspberry Pi or even the smartphone sitting in your pocket right now. It's hands down the best choice for highly resource-constrained environments.
Now, if you're in the Apple ecosystem, you probably know the traditional architecture forces data to squeeze through this narrow PCIe bottleneck between the CPU and GPU. Well, MLX bypasses that completely. It leverages Apple Silicon's shared unified memory to eliminate that copy overhead entirely. By natively optimizing for M-series architecture and AMX matrix acceleration, it outperforms standard frameworks by up to 3 times on M4 Max and Ultra hardware. So if you're doing Mac-native experimentation, this is definitely your engine.
And finally, there's Ollama. But here's the kicker with Ollama. It's not actually a low-level engine itself. It is a highly polished, developer-first encapsulation layer that orchestrates llama.cpp, or MLX, right under the hood. It gives you this magical one-click install experience, OpenAI-compatible APIs, and incredibly easy model management. It dramatically lowers the barrier to entry, making it absolutely perfect for fast prototyping, non-specialist engineers, and just everyday local usage across Windows, Mac, and Linux.
All right, jumping into sections 3 and 4, hardware-driven deployment scenarios and workload matching, let's make this practical.
We've seen the tools, right? But just knowing the tools isn't enough. We really need a strict diagnostic framework to actually apply them to your specific engineering constraints. I want you to follow these 3 steps sequentially when planning your architecture. Step 1. Map your scale. Are you just prototyping locally, or are you deploying to a production server? Step 2.
Evaluate your exact hardware. Are we talking Apple Silicon, massive NVIDIA arrays, or low-resource edge devices? And step 3, analyze your dominant workload pattern. Is it a high-throughput API with thousands of users hitting it, or is it complex, multi-turn RAG?
If we follow the logic paths of this architecture decision flow, we start right at the top. Is this for a production server? If no, you ask about your hardware. If you're on Apple Silicon, boom, you immediately choose MLX. On low-resource edge devices, llama.cpp is your engine. Just doing some rapid prototyping across platforms, Ollama is your best bet. But what if you are on a production server?
Well, that brings us to the production server crossroads. When you're relying on heavy NVIDIA infrastructure at scale, the decision pivots entirely on the shape of your traffic.
For standard high-throughput APIs, where your main goal is raw concurrent volume, vLLM is basically mandatory. Its page detention maximizes that throughput natively. But if your workload is heavily dominated by retrieval-augmented generation, RAG, or autonomous agents or multi-turn chats, then SGLang offers massive cost and speed advantages. And that's because its radix tree caching stops you from recalculating the exact same document prefixes over and over again.
When we map these frameworks strategically based on deployment scale and hardware, the territories become really clear. MLX is highly specific to Apple hardware on one side of the spectrum. Ollama and llama.cpp cover your universal cross-platform deployments. Meanwhile, vLLM and SGLang totally dominate the high concurrency enterprise production scale. The takeaway here? There is no singular best framework. Your selection is dictated entirely by your position and your specific hardware reality.
Which leads us perfectly into Section 5, the Enterprise Hybrid Strategy. Look, as we look toward the horizon of 2026, engineering intelligence takes precedence over this endless search for a single magic bullet. Novices often try to force one framework to just do everything, right? They try to make vLLM run perfectly on an edge device, or they try to push massive API volume through a llama. But the mature enterprise standard is to bifurcate the backend and intelligently route tasks across a hybridized cluster based on exact computational needs.
So check out the 2026 Enterprise Hybrid Stack. This is the culmination of our tutorial today. You pair Ollama at the bottom for rapid local development and testing by your engineers. Then, your intelligent routing layer sits in the middle. When a request comes in for raw, high-volume throughput, it routes straight to the vLLM cluster. But when a compute-heavy RAG query or a really complex agent task hits, it routes instantly to the SGLang cluster. And that is exactly how you achieve ultimate performance and cost efficiency simultaneously.
I really want to leave you with this final mandate for AI architects. Your infrastructure layer must remain flexible. You've got to match the engine to the exact hardware, the load profile, and your business logic. Framework boundaries are blurring fast, and with new hardware like Apple's M5 and NVIDIA's Blackwell arriving, flexibility is simply your ultimate performance metric.
So, knowing the massive performance gains that are literally just sitting on the table and having seen the decision flowcharts, what's the very first architectural change you are going to make to your LLM engine room today? Are you going to audit your current GPU utilization, or maybe start building out your hybrid routing layer? The blueprint is in your hands now. Thanks for joining me for this explainer, and I'll see you next time.